All right, I want to take a look at question number 2 from our homework on page 491. It's a challenging question. It's a challenging question, but it doesn't have to be overly challenging. We got to think logically about this. Too many of us, when we see a question like number 2 involving funny angles, and hey, it looks a little bit different than maybe a question that we've seen before, we panic. We get scared. And you know what happens when we get scared? We mess up. Okay, don't be scared. If you're an athlete and you're a basketball player and you're down by 1 point and you get the ball with 1 second left and you got a chance for a 12-foot jump shot, what's going to happen? You're going to mess up if you're scared. You can't be scared of it, right? You can't be scared. Hey, sometimes you're still going to mess up. Lots of times you're still going to mess up, but you're always going to mess up if you're scared of it. So let's have some confidence going into this. You guys know exactly what to do for this question. Exactly what to do. Doesn't mean you're not going to make a little mistake somewhere, but you know conceptually what to do with this question. Let's draw it out first, okay? We got a 1,200 kilogram car attempting to run a red light, strikes a stationary 1,350 kilogram car waiting to make a turn. So let's draw this here now. We have our 1,350 kilogram car. I'm going to call that car number 2. The 1,350 kilogram car is at rest. So I'm going to make it 0 meters per second. And it says after the collision, the 1,350 kilogram car goes at 8.3 meters per second, 55.2 degrees east of north. So car number 2 is going up this way, 55.2 degrees east of north, right? East from north. This is north. We're going east from north. Car number 1, it says, goes at 12.8 meters per second, 36.8 degrees west of north. This was 8.3, and this was 12.8. And then it says, what was the velocity of the 1,200 kilogram car, the car number 1, just before the collision? So car number 1, we're going to predict is going to go up this way. There's a couple people that did not do an X component because they assumed that it was going on the Y-axis. Does it tell us that? Does it tell us that this car is on the Y-axis? No, it doesn't. Now, as it turns out, it is on the Y-axis, and no X-axis involved here. It works out that way, but we don't know that when we start the question, so we don't want to make that assumption, because if that wasn't the case, then the people that assume that end up getting the wrong answer. We're going to assume X and Y components here. It's a 2D collision. We're going to assume X and Y. So let's do our thing. We got our picture. Tell me what you know about this question. I forget about numbers here. I couldn't care less about those numbers. What do I know about this thing? Tell me something I know about it. Okay, and I got to get rid of funny angles. Okay, tell me something else I know about this. Besides the fact that there's funny angles, which is important. Very important. Everybody knows something about this. John, what do you know about this? Mass 2 is an initial velocity of 0, okay. Okay, we're not looking at numbers so much right now. I mean, that's true. We have some other numbers there that are very important. But I want to look at bigger picture right now than just the numbers, okay? I want to see the forest right now, not the trees. Hey, tell me something else. Hey, again, not so much the givens and stuff. That stuff's really important. I'm not discounting that at all, but that's not what I'm concerned about right now is the numbers or the givens or what I'm looking for. Okay, what do we know? We got funny angles. We have to deal with the funny angles. How do I deal with it? Who cares right now? We'll deal with that later on. We got to deal with them. What else do I know about this question? Okay, there's a collision. And what do I do when there's a collision? Conservation of momentum. Okay, what else do I know besides the fact that there's funny angles? So I got to deal with those. There's conservation of momentum. What do I got to do when I've got funny angles along the lines of conservation of momentum? We got to do 2 components, right? An X and a Y component. If I have something with a funny angle, or even just a T-bone collision like this, then I have to do X and Y. So what do I know about it? Funny angles. I know that I've got conservation of momentum. And I know that I've got X and Y components. You don't need to necessarily write this stuff down as you're doing a question, but keep it in the back of your mind. Again, big picture. This is the stuff that I've got, that I know about this question. Now, those numbers, those givens, those are extremely important. And what I'm looking for is extremely important. But I don't want to lose sight of the big picture by looking at just those numbers, okay? All right, I'm gonna leave that up there, even though if I was actually solving this on a test, I might not write that down. Let's get rid of those funny angles here first, okay? Let's get rid of number 1 here. Draw it over here. I got 36.8 degrees. I got X and I got Y, and this is 12.8. So let's find the X component. Which side of the triangle is the X component? Sorry? Opposite, so I'm going to use the sine function for that. Sine 36.8 degrees equals X over 12.8. What's X equal there? Does anybody have that? 7.66, thank you. 7.6675, thank you. Better to go 4 decimal places than 2, right? And now let's say cosine 36.8 degrees is equal to Y over 12.8. What does that one end up equaling? 10.2494, thank you. All right, there's the first one. And now I can replace this if I want, which I do, with 7.6675 and 10.2494. Is that 2494 or 7494? There you go. There's object number 1. It's not really going left and up, right? But it's like it is. Now we get rid of the second funny angle, 55.2 degrees. Let's do that right here. This is X, this is Y. This is 8.30. It's going to be sine for X again, isn't it? What's X equal there? And the Y component is cosine. What is it? 769. Thank you. Okay, there's the other one. Whoops. Which I can replace the 8.3 with, right? Once I've replaced the 8.3 and the whatever the other one was, 12.8, like they're gone. We don't pay any attention to them whatsoever. They're completely gone now. 6.81554. The second one is 4.73. You know, the first thing that Connor told me when I said, like, what do you see here? Like, what's going on here is funny angles, right? He didn't tell me details. It's not what I was looking for. Like, I don't want you to be thinking of all the details when you look at the question. I want you to be thinking big picture. You start thinking of too many details and you're going to forget about big picture, right? You're going to miss the big picture. Connor told me it was a funny angles I had to get rid of. Okay, then I'll worry about going and get rid of them. It's like, you know, you're building a house, and like, what do the workers do, the construction workers do, the contracting company do when they build a house? Well, they don't just go straight into the, you know, foundation's poured, then they just take a bunch of wood and start hammering nails in, right? Like, they look at the big picture, they look at the plans, and they're like, all right, okay, I could see, okay, I gotta, these stairs, well, I got to make sure that I get this done, and I got to make sure that I get that done. But they're looking at big picture, right? They're not saying, how many nails am I going to need to put in that third step? Right? Like, that's the little things. We'll figure that out as we go. Okay. All right. What else to say we got to do? Conservation of momentum, right? In X and Y components. So let's do that now. I'm going to actually get rid of this. So I got some more space to work over here. Got my picture drawn, so I don't need the question up anymore. Okay, X component. Okay, this is where I saw some blanks on people's pages. There's no reason to have a blank here. You know what to do here. This is a collision. You know you've got to go X component, Y component, and you know you've got to go PI equals PF. Because it's a collision. The momentum is conserved in the X component and the Y component. Connor? On a multiple choice, no. On a multiple choice, it's right or wrong. But on the written response test that you have, absolutely. Yeah, you show work, you get marks. It's like more like physics 20. We give you a few of those written response tests because I do want to see that process too. Unfortunately, the nature of the beast is, you know, the bulk of your evaluation is multiple choice numeric response because that's what we got to be ready for, right? But I still try to give you some other just so you can express yourself a little bit more. So PI equals PF. Hey, how many objects before? We've done this a million times. Not necessarily for a question like this, but how many objects before? There's two of them. So we're going to say M1 V1I plus, well, actually, we'd say 0 here. How come? Because object number 2 is at rest, right? The initial velocity is 0. Equals M1 V1F plus M2 V2F. Man, I would love it if both of these masses were the same, but they're not. M1, 1,200 kilograms times V1I, we don't know what that is, equals 1,200 times, tell me what V1F is. Yeah, good, -2, -7.6675. Boy, I sure hope you don't forget a negative. But if you forget, if that's your mistake in this, especially right now, I can live with that. Yeah, I can live with a mistake there instead of leaving a page blank. I'd much rather see a mistake there than have a blank page because you didn't try things. M2 is 1350. And what's V2F? What's V2F? So what do you think for V2F? X component. About 16. Just look up here. Good. It's 6.81534, right? Okay. What do we end up getting for V1I there? I don't know what it is, but I do know that it's a really, really small number. It's like 0.000 something, something, something. I think there might be 4 zeros, actually. I don't even care what it is. It's a small number. What does that tell us? Ethan, what does that tell us? The fact that we got a really small number for the x component of the initial velocity? It's not, it doesn't matter. It's not moving on the x-axis really, right? In fact, it's probably supposed to be exactly 0, but there's a rounding thing in there somewhere. All right, so let's do the y component. Clearly, that's going to be more important. Listen, we know that it's pi is equal to pf. We know that there's two objects, m1 v1I plus 0, because object number 2, somebody said it. Is that rest? Matt, I think it was that said it, right? Is that rest? m1 v1f plus m2 v2f. 1,200 times v1I equals 1,200 times, all right, who's up? What's v1f? Brandon, what's V1F there? Just looking at this, object number 1, Y component. Good, excellent. 10.2494. The X component was negative, but the Y component is positive because it's up. 1350, and then V2F is what, Tyler? Good. And we solve for V1I here. Ethan, do you have the value of that one? V1I, do you have that? Thank you. 15.6 meters per second. Listen, if you got an X that's almost 0 and a Y that's 15.6, what's the answer? 15.6. Listen, you want to resolve those into a triangle, which technically I guess we should. You got 0.0000 something on the x-axis, and then you get 15.6 on the y-axis. Take the hypotenuse of that. What is it going to be? No. Hurts too much. What's it going to be? 15.6, right? Just like that question yesterday we did with the coal hopper. Different question, right? But in the sense that one of the components doesn't really matter, just that this time we didn't know it didn't really matter until we did our calculations. All right? I would like you to have a look at this question now, please, on page 15, I believe, of your worksheet booklet. This is the setup for it, and then the question follows it, question 17, what's the magnitude of the momentum of the third piece of glass? So basically, this ornament explodes into 3 pieces. We want to find out what the momentum of the third piece is. I want to draw your attention to one little thing first that you may find a little bit challenging, and you may find it challenging because you haven't seen something like this before. We see this question as 2 angles, 60 and 120. Notice that they both point to the same object, object B. You see that? It's like saying, where's Megan? Megan's 3 meters from the front of the room. Megan's 5 meters from the back of the room. We're describing her position 2 ways. We don't need to describe her position 2 ways. One is sufficient. We have 2 angles here that describe object B. Do we need both of them? No. Well, which one do you want to use then, 60 or 120? Probably the 60. But just a little note here. Okay, let's say you said the 120. Whenever take your calculators out right now, try one little thing. Go sine 60. Sine 60 is 0.866. Go sine 120. 0.866. Go cosine 60. Should be 0.5. Go cosine 120. Should be negative 0.5. So it doesn't really matter which one you do, but it makes more sense, I think, to go with the 60 because you can resolve it with that little triangle, right? A lot easier. It's easier to visualize. I would scratch that 120 out completely. It describes the position of object B in exactly the same as the 60-degree does. All right? All right, see what you can do. And remember, there's a forest here, okay? There's a forest here, not just a tree. All right, let's have a look here, guys. Hey, what's the first thing that we kind of spot here? There's a few things that we know about this before we worry about givens, right? Forget about 212 grams, whatever. I don't care about that. Okay, what do you notice? Yeah, tell me something, Matt. Okay, there's an explosion. What do we do when there's an explosion? Anytime we have an explosion, we know that momentum is conserved. So we know that we can do conservation of momentum. Let me write that so you can understand what I wrote. Conservation of momentum. All right. What's kind of special about this conservation of momentum, Kenneth? Okay, there's no initial momentum. Maybe I'll write that down. Okay? That's kind of a given, but that's something that we need to know too. It's a little bit smaller picture that I want to see here right now. Okay, but in the end, it's still important. Big picture stuff. Conservation of momentum. What's different about this versus the questions we did a week and a half ago? Okay, there's three pieces to it again. Like, don't get focused on those details right now. This is two dimensions, right? This is a two-dimensional thing. We got an X component and we got a Y component. What's the other thing that kind of jumps out at you? Boy, I sure hope it jumps out at you after what we've said over the last couple of days.
It's an explosion.
Yeah? The conservation of momentum. Somebody said it. The angles, the funny angle. Right? I got funny angles. So let's deal with that funny angle first here, okay? Okay, object B is going over here. This is X, this is Y, this is 60 degrees. And we said before that really it doesn't matter whether you use 60 or 120, but it's easier to deal with the 60. It makes us feel better. What's the hypotenuse here? Yeah. What is this thing down here, 1.91? Huh? Yeah. And do this in your calculators, please, right now. 0.212 times 9. 0.212 times 9. What do you get? 1.91. Go figure. Go figure. When they tell us the mass is this and the velocity is this and the momentum is this, they agree with each other. Go figure. What are they doing here? They're trying to make life a little bit easier for me. They're trying to say, look, you can use the velocity and the mass if you want, but ultimately we're going to multiply m times v, right? Well, then why don't we just use the mass m times v that they give me? Make sense? They're saying, look, why don't you find the x and y components of the 1.91? Now, if you want to do it with velocity, and I know a lot of you were as I was walking around, and I didn't stop you because that's absolutely fine. I was going to show you how much shorter it is by doing it with momentum. Can we do x and y components of momentum? Is momentum a vector? Yes. Could we do x and y components of kinetic energy? No. Why not? Because it's a scalar. If you got a vector, you can do x and y components of it, momentum included. Cosine 60 degrees is equal to x over adjacent over 1.91. X is going to end up equaling 0.955. And remember, that's momentum, kilograms meters per second. Sine 60 degrees is equal to the opposite side over 1.91. Y ends up being equal to, what do we got here? 1.91 sine 60. 1.6541, thank you. So now that we've got these x and y components of the momentum, we could have done that with velocity, but we chose to do it with momentum because we want to save ourselves a little bit of effort. Right? They multiplied mv for me. Now let's do x and y components, right? We know what to do. Pi equals pf. We know that the initial momentum is 0 because it's not moving. We would say m1 v1 f plus m2 v2 f plus, no, we'd say m3 v3 f, right? 3 objects after the collision or the explosion. Now, look at this. Look at this. What's m times v? 2.52. We didn't need to go 0.168 times 15. We know the momentum already. What's the x component of this momentum? Negative 0.955. Plus the final momentum of object number 3. That makes sense? Now, most of you did it with M and V, and you found V3F. That's fine. What would you have to do to get the final momentum if you found V3F? Multiply by mass. I don't have to do that because I'm solving for momentum right now. Does that make sense? Okay, I'm not going to actually solve that because I'm going to let you get out of here. That's P3FX component. We do the same thing, though, with the Y component. We'd say 0 is equal to 0, because that's only on the x-axis, plus 1.6541. If you found the Y component of the velocity instead, it would be m times that component, but I already have momentum here, so I don't need to multiply m times v. solve for P3F for the y component, well, then we know what to do, right? Then we got our x component, we got our y component. Let's do the Pythagorean theorem. When you do that, hey, when you do that Pythagorean theorem, x will be negative, by the way. So will the y component be negative. When you do that, what are you going to get here? Is this speed, velocity, or momentum? This is momentum with the way that I did it, right? With the way that some of you guys did it, what do you end up getting here? Velocity, and then what are you going to do to get momentum, which is what they ask you for? Times it by the mass. Does that make some sense?